It's Autodidact. We're back. Day number 4 of our 30-day challenge. Today we're getting into some actual mathematics, a little bit of linear algebra. I'm going to try to make a short little presentation because I got to make 30 of these. So I'm going to try to condense an insight I've had in the field. And then we're going to go to an old book by De Morgan, written in 1842 that I stumbled upon yesterday, and I'm going to start reading. A lot of old words in there. They spelled show as shoe, S-H-O-W. They spelled S-H-E-W. 1842. It's a long time ago. All right, I'll see you at the library.
I am on a quest to understand and master high-level mathematics. I tried university to get this done, but it wasn't the answer. And so I've left it to venture out on my own to find the knowledge I desire. Self-educating, using whatever resources I can find, documenting my journey as I go in order to help you in yours. The mountain is high and the path is long. So let's get to climbing.
Okay, so yesterday I was looking for a book in calculus, more of like an older book on it, and I saw De Morgan, which is a name I remembered from calculus class, De Morgan's Law, and I was like, oh, this is probably cool, probably a reprint. I don't know if you can tell. Not a reprint. Literally, this is from like 18 something when this was written in there, I'm pretty sure. Look at that. Look at that handwriting. I don't even know where this book came from, but like ancient we're talking. Written by literally De Morgan, printed when De Morgan was still kicking. I was trying to find a date in it. Okay, that says 1879 to something. I think this was in a library of somewhere, from 1879 to somewhere else. So I was looking through it, trying to find when it was printed. Found the preface to the second edition, 1842. It's printed 1842. I saw a handwritten quote in the beginning of it by Lord Kelvin. Oh, where's the quote? I don't know if you can read that. Lord Kelvin said, "The reason why De Morgan's great book on the differential and integral calculus, which he valued highly, was now less valued than formerly, was because it is too good for examination purposes. Life by somebody." That's about Lord Kelvin. Someone needs to say we gotta read it, because that's just absolutely goated. Presentation time. So I'm going to give a fictitious yet pertinent approach to how matrices were invented. It works logically, it's not how they actually came about. It might be, I haven't looked at the whole history, but I found this a useful heuristic for learning mathematics, is kind of make up some hypothetical history that's logically based, and then when you go back and learn the actual history of a topic in math, it's like way more of a pain in the ass. Like, usually some genius came along and then everybody's operating here and then they went like, how about this thing? And then it makes absolutely no sense because they're like just stupidly smart, and so the plebs have to come along like us later and then figure it out. But there is usually a logical step to take, and that's what I'm gonna give here. Today we're talking about matrices and what they actually are. I never understood this. I've taken a lot of linear algebra, but never understood what we were doing with matrices. I understood the rules of manipulation, but what they actually were doing, how to think of them, totally had no idea. And so after a lot of digging, it turns out that they're actually like pretty simple, how they evolved, and there's a few logical steps you can take to get there. So I'm gonna take you back, starting with functions. If you're watching this, you probably know what a function is. Single variable, y goes f of x, you know. One number goes in, one number comes out, Bob's your uncle. So you can think of it like a machine that takes in numbers and spits out numbers. There we go. And then this evolves over time. You know, some mathematician comes along and he's like, all right, okay, I see you one in, one out. Why don't we, I don't know, send two numbers in? Why don't we send two numbers in and see what happens? Two numbers in, one number out. And everyone's like, I don't know, dude, that's kind of crazy, dude. Like, functions are working with the Cartesian, you know, they were doing this thing, has to represent it, and you have functions, that's one-dimensional. You know, what even is a two-dimensional function? And this was probably a big leap, maybe, I don't know. Two numbers in, one number out. That's the function box now. And you probably know what it represents this. It's like or something like that. So it's the height. That's better. So this is z, x, y, z, and then you represent it as like height is determined by where you are on the plane. And so that's all well and good. Then somebody else comes along And he says, why don't we just make it n-dimensional? Why don't we have like 45 inputs to one output? And everyone's like, dude, that's crazy. You're crazy, dog. You're wilding out, bro. What are you talking about? How are we going to represent, like we have 3 dimensions. That's like a 45 dimensional function. What are you talking about? And so you represent that like, I don't know, like y equals f of something like that. But you still have, at the end of the day, you still have one output number. There's one number being output, a bunch of numbers being input. So then some absolute madman, descends from the mountain and he goes, guys, I want to try something out. Up until now, you've been in one paradigm, right? You've been thinking one output number, throw a bunch of stuff in, but one number comes out. One number output. You're not thinking big enough. He's like, all right, why don't we try, hear me out here, why don't we try having multiple numbers output as well? And of course that caused mayhem. Everyone's like, you're a fool, you're a charlatan, throw this man in the nut house, he clearly needs help. But he's like, hear me out here, hear me out. So right now, he has a room full of people that's gonna decide his fate, and he's kind of like, okay guys, look. Right now you have, you accepted that you can have like n-dimensional functions and then one output, right? But what if and let's take the simplest case, what if instead of having one output, how could we have it so that we have 2 inputs and 2 outputs? How do we do that? 2 inputs, 2 outputs. And so it turns out, the easiest way to do this is to just say, go like this. So you want 2 outputs, right? And so let's say that we're just coming up with this arbitrary notation. We're just trying to come up with something. We haven't operated with this before. We're just trying to say, okay, how do we represent this 2-dimensional output? It's a whole new thing, right? So he does this. He comes up with this thing, and he's like, okay, we're gonna put the first equation up here. We're gonna say x, y. Let's say g of x, y. So we're gonna come up with a new notation because how do you put 2 numbers as an output to a function? It's all very strange. We're gonna have this as what are we gonna call these? I don't know. What's a symbol I can use? ZW. Let's say ZW. Yeah, we can use ZW or WZ. Do you feel like you just created a new branch of mathematics? Because you did. Bam. Multi-dimensional outputs. So we have a vector from a vector. So this is a way of representing a multi-dimensional output and input. So you have 2 variables, x and y, coming in, and you have 2 variables coming out. And there's another way of representing this. Let's go, because this is, I don't know, kind of hair. We've just invented this on the spot. So over time, we want to put it in normal function notation. And so instead of that, we're going to have, let's say just put f here and g of here. These are functions. We're going to have, maybe put them like that. I don't know. Kind of poor notation, but we're working with notation here. So it's all good. We're inventing notation. And then because we have 2 inputs going in, we're gonna put them like this. And so all this means is like, go like this, right? So f of something and then find out whatever that is, and g of this and find out whatever that is. And so we're gonna say equals, yeah. So that's how you represent multi-dimensional outputs for multi-dimensional inputs. And then hopefully you're noticing some similarity between this and matrices. We're almost there. So matrices are just this, and with this you can go, I don't know, you have like 20 inputs and 20 outputs, or like 2 inputs and 14 outputs. Like you can make these crazy stupid. But at the end of the day, it's a function. We're operating with functions. Think functions. It's a function. And so all a matrix is. Oh, also, there's a way of representing this thing. Watch 𝘽𝙡𝙤𝙢𝙧 Linear Algebra Series. It's like you take so say it's a two-dimensional. It's a 4-dimensional thing what you're operating with, but you can kind of take the original graph, superimpose a new graph on top of it, and then wherever the lines go, that becomes like the new point. So it's like the function takes the point 1, 1 and moves it to like 13, 14. It'll like move it over there. But watch 𝘽𝙡𝙤𝙢𝙧, you'll see what I'm talking about. I don't have the technology at this point to do my own. Okay, so then the only next step we gotta do is limit this to linear equations. So a linear equation is any equation that just multiplies it by some number. So y equals sine of x, not linear, not multiplying by some coefficient, right? It's not just a nice easy y equals blank of x, it's y equals sine of x, it gets all curvy. Wrong, incorrect, not linear. Y equals e to the x, not linear, unfortunately. Y equals 4x, hold on, that's linear. Linear, because it's a line. It's a line. And also coefficients aren't allowed. I had a big problem with this, like, well, what about y equals 4x plus 2? What about that? And that actually turns out not to be fitting our thing. There's a whole, I dove into this, why that's the case, it's very complicated, but just this, you're not allowed to have like plus 2's on it. Some number multiplied by the variable, that's a linear function. A multidimensional linear function equals, so it's just coefficients multiplied by the variables. So this is, yep, that's good. If A and B are just normal numbers, or not normal, just numbers. It doesn't need to be normal numbers. Just real numbers, sorry. But this is no good. That's not linear. That's not linear, unfortunately. Not linear. Does not make the cut. Okay, so you have linear numbers and you have multidimensional functions. Or sorry, you have linear functions and multidimensional functions. Linear functions, multidimensional functions. Peanut butter and chocolate time. You ready? Bring them together. What do we got? What do we got? What we got is matrices, baby. When you see a matrix, think function. Matrices are functions. They take in vectors, they spit out vectors. Vector comes in, spits out a vector. So matrix is just this or some larger version of this. So maybe it's like, it could be 3 long, it could be arbitrarily long and take in arbitrarily sized vectors. But at the end of the day, it's just a way of doing multidimensional linear outputs. So it takes a vector in, it spits a vector out, and it does so linearly. That's the trick. It's a way of doing multidimensional functions, and the only restriction on that is it's linear. It's a linear way of doing it. So that does I erased it, but it multiplies every variable by some number. Because it just does the linear thing, there's an easier way of representing it. You can just put the coefficients in the actual function notation. And so we do that by so what this says, that took me forever to understand, this is just a function. It's just a function. And it takes in this thing. This is the argument. This is the argument, and this is the function. This says, take this, right, x, y, z, take x multiplied by 1, take y multiplied by 2, take z multiplied by 3. Same thing for this row, take 4 multiplied by y, take 5 multiplied by, take 4 multiplied by x, sorry, take 5 multiplied by y, take 6 multiplied by z. And we just invented this. We invented this notation, this way of multiplying it. It's just a way of doing it. Come up with your own way of trying to take a vector as an input and have a vector as an output. Just to see how you can do it. There's a ton of different ways to notify it. This is just one we've come up with, but it's just an arbitrary way of writing it down. And so this is a function. You see a matrix, think function, multidimensional in, multidimensional out. And they don't have to be square, so you could have, you could have it like, so this one would take, now. So this one would take 2-dimensional input, a 2-dimensional vector, you fire it into the function, and it outputs a 4-dimensional vector. Because it has 4 different things, so it'll have like, I don't even know, it would be, so this is a 4-dimensional vector from a 2-dimensional vector, and you can reverse it. You could have a 4-dimensional vector come in, 2-dimensional vector come out. You could have like a 37,492 sized vector come in and like a 49,000 vector come out. You can get crazy with it, and the study of linear algebra is just a study of these functions. So there's a bunch of stuff you can do. It gets quirky, and there's a bunch of different eigenvalues, eigenvectors. Like determinants, I hate determinants. Determinants are my mortal enemy. Not a fan of determinants, but you get the point. But linear algebra, when you look at linear algebra, it's just a study of linear multidimensional functions. You take in a vector, you linearly do something to it, and you fire another vector. I was intending that to be like 2 minutes long, but this is gonna be a pain in the ass to edit. It needed to be said though. I'm gonna do a whole series on linear algebra, so if this got confusing, I'm gonna try to do it a little bit better in the future. But when you see matrices, what I really want you to understand from this, the one main thing I wanna get across is when you see a matrix, it's a function. See a matrix as a function, and that should clear up a lot of stuff. It did for me anyway. All right, maybe I do an outro, maybe I don't. If I don't do an outro, I love you guys, take it easy, and Godspeed. I will see you in the next one, which is tomorrow. Boy, do I have a lot to edit tonight. Holy cow.